Okay, so back to the warm-up here. What can we do 2 times in a row? Could be add, subtract, multiply, divide, anything that will turn a 2 into a -2, a 3 into a -3. Jeremy said multiply by the square root of -1. Let's see if that works. 2 times the square root of -1 times the square root of -1 equals what? Well, what would the square root of 1 times the square root of 1 be? What is this little property? The square root of a squared is equal to what? It's equal to a, right? That's a little property that we've been using last week. The square root of 3 squared is 3. The square root of 4 squared is 4. So the square root of -1 quantity squared should be -1. And what's 2 times -1? Did that work? Shouldn't that work with n as well? Let's see. N times the square root of -1 times the square root of -1. That equals n times -1, which equals -n. So congratulations, Jeremy. Did anyone else come up with something? Just Jeremy? Jeremy, how did you think of that so quickly? What do you mean you don't know? It just popped in your head? You're just that gifted? Well, guess what? That earns the Corpy Superstar pencil. So help me sing the pencil song to you. You know the pencil song, right? You know the birthday song, right? So you know the pencil song. Ready? 1, 2, 3. Happy pencil to you. Hey, happy pencil to you. Oh, happy pencil, dear Jeremy. Happy pencil to you. Wow. Thanks for thinking outside the box. Yeah, this gives us an algebraic tool that we can use. The square root of -1 times the square root of -1 is -1. We do it twice in a row, and that allows us to take a positive number and turn it into a negative number. Now, I also heard another word come out of Jeremy's mouth. The square root of -1, you said, is equal to what? Yeah, it's equal to I. Now, do you remember that from Algebra 2, or do you study that on your own, or do you just remember it from Algebra 2? Yeah, we're doing it right now in Algebra 2. So I know everybody's seen this in Algebra 2. It probably just didn't pop into your head. Now, today we're going to learn about what that actually means. What is an imaginary number, and what does it mean to multiply something times I? All right? What does that mean? Very good. Okay, first of all, this section is complex zeros of polynomials. In the previous section, we were looking at real zeros of polynomials. Real zeros. What do we mean by real zeros? You can find them? How do they appear on the graph on the real number line? What's another name for zeros? Roots. They're the x-intercepts. So they're real in the sense that we can actually see them. We can visualize them as x-intercepts on the graph on the real number line. We call the real number line the Cartesian plane, right? Y'all remember the Cartesian plane, or do you just call it the coordinate plane? Y'all have heard the Cartesian plane, right? Named after Rene Descartesian, right? You can see on this poster here, it has the 4 quadrants around his head because he's the guy who came up with the coordinate grid system on the real number line. We have x real numbers on the x-axis and y real numbers on the y-axis. So we can see real x-intercepts. In this section, we're going to learn about complex zeros of polynomials. Now, what are complex numbers? Let's look at it. The complex number system is this. We abbreviate it with the letter C. Just like the double bar R is a set of real numbers, the C is the double bar C. It means the complex. And we have to use set builder notation here. So the form A plus BI, where A and B are real numbers, and I is called the imaginary unit. Okay, so a complex number is of the form A plus BI, where A and B are real numbers and I is the imaginary unit. A is called the real part, and BI is called the imaginary part. Now let's give some examples of complex numbers. First of all, the complex numbers are the largest number system that mathematicians use. Okay? It includes all the real numbers and all the imaginary numbers and all the combinations of them, right? So this is we're just going to touch the waters of imaginary land here, and then we're going to go back to real numbers for the rest of the year. Somebody give me an example of a real number. 1, 2. Let's combine those and call it 12. Okay? 12 is a real number. It's on the number line. But would you believe that 12 is also a complex number? Because I can write it in the form A plus BI. It would be 12 plus, and if there's no imaginary part, guess what the B value has to be? 0. Yeah, 12 plus 0i. If you can write it in the form a plus bi, it's a complex number. So can't we do that with any real number, say plus 0i? Yes, so guess what? Is every real number also a complex number? Yes, okay. What about the imaginary number by itself, the imaginary number I? Is I a complex number as well, or is it just purely imaginary? Well, it is purely imaginary, just like 12 is purely real, but it is also a complex number. Yeah, what would the a value, the real part, have to be if there's no real part? 0 plus 1i. Yeah, there you go. So you have all real numbers being complex numbers. You have all purely imaginary numbers, which we'll talk more about here in a little bit, are also complex numbers. And then you have numbers like 1 plus I. 1 plus I is purely complex. It's not entirely real. It's not entirely imaginary. It's a combination of the two, okay? And there is a complex number system and a complex plane on which we graph these just like we have a real plane, okay? We're going to talk about that in a little bit here. Now, if you read this Calvin and Hobbes comic up here, I don't think Bill Watterson makes these anymore, but they were funny back in the day. Hobbes is always really, really smart. And he just has intelligent ignorance. He just doesn't know that he's not supposed to know these things. He knows what imaginary numbers are. But in his mind, look what imaginary numbers are. 11, 30, 12. Those are purely imaginary numbers. They don't really exist, right? Those are imaginary numbers. What if I told you that imaginary numbers are like I and that they really do exist? You'd be like, then why do we call them imaginary, right? Where were imaginary numbers first encountered? It's a good question. A long, long time ago, when people first started doing math, ancient Greece. Heron of Alexander, sometimes called the hero of Alexander, he first came across, when he was trying to find the volume of a truncated pyramid, he came across the square root of a negative number. And he scratched his head, because they were working with real numbers back then. And he didn't know what the square root of a negative number went. So he fudged it, and he moved on. Right? He's just like, whatever. I got it on a Monday. It's a bad number for a Monday. We'll just move on. And Tuesday came around, and they forgot about it. Well, they didn't really forget about it, but it peaked its head again when all these Italian algebraists who were trying to find the roots or the zeros of these polynomial functions, which is what we're studying right now, they were trying to find formulas for finding the roots of polynomials. If you look on the back board right there, there's the formula for the quadratic. That was already well known. But they were trying to find explicit formulas for the cubic and for the quartic, and then they proved later on that they couldn't be found after that. So they came across the square root of 0. The first guy to do it was this guy. Anyone know a guy these days named Scipione? Who are you going to prom with this year? Scipione? Scipione del Lamborghini? No, Scipione del Ferraro. Oh, okay. That guy. I forgot about him. He actually came across square roots of negative numbers as well. But he didn't know how to deal with them. So guess what he did? He called them impossible solutions. Impossible solutions. He was frustrated. Oh, it's impossible. I can't do it. It can't be done. Well, later on, Cardano, this guy over here on the right-hand side, and Pascal, actually, they invented probability because they were arguing over who can make more money. So they came up with a mathematical way to find odds so they could bet better, and they invented probability. Well, Cardano was also arguing with Descartes, trying to be the first guy to find the solutions to these polynomials. Oh, we got a message. Oh, he's yeah. We'll try again when he shows up. He's absent today. Yeah. I did. I changed it this morning. Yeah. I like to change it every day. They were arguing in the late 16th century over who could find the zeros. Well, Descartes had a lot of influence. He was well known in other realms besides just mathematics and gambling. And he actually called the same types of numbers that Ferraro called impossible. He called them imaginary. So he kept with the I theme, right? Impossible, and now he called them imaginary. But when he called them imaginary, he meant it derisively, like Ferraro did. He's like, oh, stupid imaginary numbers, you stupid heads, imaginary dum-dums, right? But because he had so much influence, the name stuck. So even later on, when guys like Euler and Gauss started working with them and realizing that they were actually very, very, very real in the sense that they exist, the name imaginary had already stuck. Okay? So Euler, the great Leonard Euler, who's down below to the left in 1777, he gave us the symbol I to represent the imaginary unit, right? That's not a real far throw from the impossible and imaginary, right? Hey, why don't we just use I, the first letter of both of those words? So we used I for the imaginary unit. And then it was Gauss, who's in the red poster there next to Descartes. He kind of took it and ran with it. He's the guy who came up with this theorem right here, the fundamental theorem of algebra. Okay. Now, funny little story about Euler. The great Leonard Euler is found down here, and he looks like me the other day when I dressed like a dad chef. He looks like he's wearing the chef hat like I was the other day. Notice how he's squinting his left eye. He's the most prolific mathematician of all time, single works mathematician. But he did most of his breakthrough work after he went blind. He had two eyes, and he worked and he was pretty good. But then he lost sight in his left eye and produced even more works after he went blind in his left eye than before. And people were just astounded by that. Because like most people, if they were to lose sight in one eye, they'd just be like, oh, it's been a good career. I think I'll just, stick to napping on the left seat, whatever. But he actually became more prolific. And they asked him how, and here you could tell he's a funny guy by looking at him, right? You know what he said when they asked him how he was more prolific after he went blind than before? He said, it's easy. I was less distracted. He was less distracted. He had one less eye to look at him. Funny dude. Brilliant dude and a funny dude. Okay. Gauss went on to prove this right here. When he was 22 years old, he earned his first PhD by proving the fundamental theorem of algebra. And he loved it so much, this theorem was his best contribution to mathematics, according to him. He came up with 3 different proofs over the course of his lifetime to prove this theorem. And the last one came 50 years after the first. That's how much he loved the fundamental theorem of algebra. Okay, let's read the fundamental theorem of algebra. The fundamental theorem of algebra. When do you usually learn fundamentals? At the end or in the middle or in the beginning? You usually learn fundamentals in the beginning, right? Usually. We are now in the second 9 weeks of your pre-calculus career. Algebra 1 was a long time ago, wasn't it? You would have thought that maybe you learned the fundamental theorem of algebra on day 1 in your Algebra 1 class, wouldn't you? So why is it coming so late in the game? Why are we learning the fundamental theorem so late in the game? Well, the truth is you couldn't have handled the fundamental theorem in the beginning because you didn't know much about algebra, did you? This wouldn't have made any sense to you if you had learned this on day 1 in Algebra 1. So what you've been learning up to now has just been the mechanics of algebra. You've been learning the skills, how to manipulate numbers and to combine like terms and how to factor and to do all the mechanics that drive the theory of what algebra really is, which in this case is to find complex roots to polynomial functions. You're now able to know what this means, and you're now able to use it, okay? Let's read it. Here's what it says. It's pretty simple. It's like one line. A polynomial function of degree n has exactly, no more, no less, n complex roots, including multiplicities. A polynomial of degree n has exactly n complex roots with multiplicities. So what does that mean? The roots are going to be what type? Real or imaginary, or possibly a combination of both? Combination of both, possibly, and including multiplicities. That means like bounces and wiggles and stuff like that. So why is that important? Well, if you think about example 1, it says to find the complex roots of x squared minus 1 and x squared plus 1. Let's look at letter A first. Based upon the chapter section we just got out of, how many roots does this one have? Can you tell me? 2. How do you know it has 2 roots? It's a degree 2, right? That's what the theorem says. It's going to have exactly 2 complex roots. Now, the section we just got out of was something like this. X squared minus 1, find the roots. What would we do? What's the first step in finding the roots? What do we have to do with the equation first to find the roots? You got to set it equal to 0. Now, x squared minus 1, you could solve by factoring if you wanted, right? It's a difference of squares, so it factors into the product of 2 whatchigates? Conjugates, right? Let's solve this one by extracting the square roots, though. There's no middle term here with an x in it, so we'll just extract the square roots. We'll separate the x squared from the numbers, And then when we take the square root, we have to do what? Plus or minus the square root of 1. And what is the square root of 1? 1. So we get plus or minus 1. Are those real or imaginary or a combo? Well, I'm sorry. Are they real or imaginary? Those are real. So we have a real way to see them, right? We come over here to -1, come over here to +1, and it opens up like that. We actually can physically see there's one x-intercept, there's another x-intercept. Now, in this case, the theorem tells us that there were going to be two complex roots. Are 1 and -1 also complex numbers? Yeah, -1 plus 0i, +1 plus 0i. But the theorem also tells us when to stop looking. How do I know to stop looking for more x-intercepts here? There's what? What's the degree of the polynomial? 2. How many did I find? 2. The theorem says that there are how many if n is the root? N is the degree? Exactly n, right? Exactly n. So as soon as you find that many, including multiplicities, these are both M1s, right? You know to stop looking. Well, this is where Faro kind of came into. This was kind of the first known existence of the imaginary unit. This is where Scorpion for Ferrari, whatever his name was, this is where he kind of got frustrated and called them impossible roots. Let's say I want to find the real roots of x squared plus 1. I would set it equal to 0, wouldn't I? Yeah. Now, x squared plus 1 does not factor because it's the sum of two squares. But I can extract the square roots, and I'll bring the 1 across, and I get -1. And then I'll take the square root of both sides, and I get x equals plus or minus the square root of -1. Now, knowing what you know, this is not much of an obstacle, but imagine discovering this way back in the day and being like, what number can I multiply twice by itself and get a negative? It doesn't really work, does it? Okay, we get the square root of -1. What do we call this now, thanks to Euler? It's the imaginary number. So the square root of -1, we get our two complex conjugate roots, 0 plus I and 0 minus I, right, Aiden? Yeah, 0 plus I and 0 minus I. Those are purely imaginary roots, but they're also complex. Okay, now how would we visualize this on the real coordinate plane? This is the real coordinate plane. What does the graph of x squared plus 1 look like? Does it touch the x-axis? What does the plus 1 do to the graph of x squared? Moves it up 1, so it looks like this. How many real x-intercepts do we see? 0, right? There are 0 x-intercepts. And you know why we don't see any real x-intercepts? Because the two solutions are what? They're imaginary. Now, the question always comes up, how do we visualize imaginary roots on the real number line? How in the heck can we visualize imaginary roots on the real number line? You think there's a way to do it? To satisfy people's curiosity, this is an explanation. Imagine a third axis coming straight off the board here from the origin. A z-axis, if you will, like three-dimensional. You got your two-dimensional here. Imagine an axis coming off straight off into my room. That would be positive z, or we'll call that positive I-axis. And then you got an axis going to Mrs. Lincoln's room the other way. If you project these two down now, this is 1i and -1i. So you would come out one distance unit into our room and put a dot, and then you go into Mrs. Lincoln room 1 unit and put a dot. And those two dots that lie on that line would be the visualization of the two imaginary units. We don't see them in 2D. It's only if we add the third imaginary 3D vector to there do we see it. But that's not very satisfying. So usually when there are complex solutions, we graph them on the complex plane, not the real plane. Okay? So how does this lead to what I was saying earlier in the warm-up about what can I do to two different numbers or do twice in a row to get from 1 to -1? And you said multiply by the square root of -1. That's exactly right. Because if I go 1 times I, that's 1i squared. And guess what I squared is equal to? -1. So that becomes 1 times -1, which is -1. Yeah. Now, what does that mean graphically? Let's skip this little example 2 for a second and come down here. There is something called the complex number plane, the complex plane. And I'll just mention this to you so you can kind of maybe understand it visually. On the complex plane, which is not the coordinate plane that we're used to, think of the real number line like what we have. Before you learned the y-axis, you just talked about the x-axis, right? You talked about the x number line. We still have the real number line on the x-axis. But now the y-axis is your imaginary line. So we're going back to 2D, but we have the imaginary on the y-axis. Okay, think of multiplying by I the first time as a 90-degree rotation. That would take a vector that has a length of 1, and it would rotate it up here, and now it's pointing at positive 1i. What if I did another 90-degree rotation counterclockwise? Where would that send me? That would send me pointing due west, which would be at what? Negative 1. So multiplying by I, or square root of negative 1, as Jeremy said in the beginning, on the complex plane is equivalent to a 90-degree rotation. And if you rotate counterclockwise, it's positive. You could also rotate counterclockwise. If you rotate counterclockwise, that would be negative I, and then you do another negative I, and you get negative 1. So that's kind of satisfying. Multiplying by I is equivalent to a 90-degree rotation. Now let's look at powers of I. If I were to keep going, a 90-degree rotation one time is I. A 90-degree rotation again is I squared, which is negative 1. What if I did another 90 degrees? Where am I pointing? I cubed, which would point straight down at negative I straight down. And if I rotate another 90 degrees, that's I to the fourth, which puts me back at what? It puts me back at positive 1 where I started. And then what would I to the fifth be? I to the fifth would be I. If I do it again, I to the sixth would be the same as I squared, which is negative 1. So on and so forth. I to the seventh would be the same as I cubed, which is negative I, and I to the eighth would be back to 1. So every time you multiply by I, it's another 90-degree rotation around the coordinate plane, the complex plane. And a positive rotation is counterclockwise. Let's look at the algebra of that. The algebra of that is what example 2 is. And you've seen a little bit of this in algebra 2, but not to this extent. Let's start right here in this table, right here. What is I defined to be? The square root of negative 1. Thank you, Jeremy, and thank you, Leonard Euler, right? Okay, if I multiply both sides by I, multiply the left side by I, and multiply the right side by I, what do I get? What's I times I? I squared. And what's negative square root of negative 1 times square root of 1? Negative 1. Okay? Now, what if I do it again? What if I take I squared equals negative 1, and I multiply both sides by I? I squared times I is I cubed. And what's I times negative 1? Negative I. All I'm doing is I'm multiplying straight across here. Okay? So what is I cubed equal to? I cubed is negative I. Remember, why does that work? Think about the rotations. I cubed is negative I. I'm rotating 3. I squared, I cubed, we're pointing straight down. All right, let's look at the algebra again. I don't think you understand exactly what I'm doing here. I'm just multiplying the left column by I each time. So if I know I squared is negative 1, let's come off to the side here. If I squared is equal to negative 1, what do I get if I simply multiply both sides by I? That's what I'm doing. I'm going to multiply this side by I, and I'm going to multiply that side by I. What happens on the left side? What's I times I squared? I cubed. And what's negative 1 times anything? Negative that thing, right? So that's negative I. And that brings us to this row right here. So I is I. It's the imaginary unit. I squared is negative 1. I cubed is negative I. And now what if I take I cubed equals negative I, and I multiply both sides by another I? Well, what's I times I cubed on the left? I to the fourth. And on the right side, I get negative I times I is I squared. But what's I squared equal to? Negative 1. So that's the opposite of negative 1, which is now what? Positive 1. Is that consistent with our 4 rotations of 90 degrees, bringing us back around literally full circle? Back to positive 1. Yeah. What is I to the fifth going to be? It's going to be I again, right? It's going to be I again, which is the square root of negative 1. What is I to the 6th going to be? I squared, which is also known as what? Negative 1. Let's do one more. We'll squeeze another. What's I to the 7th? Multiply both sides by I again. What's negative 1 times I? Negative I. Do you see a pattern repeating? We're just literally going around the circle again, right? And so we're either going to be landing at I, negative 1, negative I, or 1. Those are the 4 positions on the complex number line. I is straight up, negative 1 is due west, negative I is straight down, and 1 is due east. That's our starting point on the coordinate plane, on the real plane. And then it repeats, I, negative 1, negative I, 1. What about going backwards, Aiden? What about going backwards? What do you think I to the 0 is going to be? It should be 1, which is the same as I to the what below? I to the 4th, right? What should I to the negative first be? Negative I. What should I to the second, or the negative second be? Should be negative 1. You see how we're just repeating the pattern? We're working the pattern backwards. I to the 4th is 1, that's I to the 0. I cubed should be negative I, which is here. Negative 1. What would I to the negative 3rd be? Should be I again, right? Now, there's another way to figure this out. Watch this. If I really want to know what I to the negative 1st is, if I don't know it's negative I, what's another way to write I to the negative 1st without the negative exponent? What's that? What does the negative exponent mean? It's under 1. Good. So that's 1 over I. Now, here's what I can do. If I multiply by a clever form of 1, that is the conjugate, you did this in algebra 2 as well. You multiply by the conjugate of the denominator. What's the conjugate of I if I is really 0 plus I? What's the conjugate of 0 plus I? What's the conjugate of x plus 2? X minus 2. So what's the conjugate of 0 plus I? 0 minus I. What's another name for 0 minus I? Negative I. Right? Negative I. So if I multiply by negative I over negative I, and I multiply straight across, I get negative I over negative I squared. But what's negative I squared equal to? If I squared is negative 1. Louder. Positive 1. So what's negative I over 1? Negative I. Is that the same thing we got over here by looking at the pattern? It is, right. So that's how you can get i's out of the denominator. If you remember in algebra 2, we're doing it literally right now, complex zeros, you multiply by the conjugate, and that gets the i's out of the bottom. Okay? So far, so good. Any questions? Oh, yes. Carly, do you have a question? Oh. We are going to move on as soon as there's no more questions. Are there any questions? Oh, crap. I was not prepared for this. That's too many questions for one class. We're going to have to schedule individual times where you come in on Saturday morning. Let me pass around. I'm going to pass around a note card, and you write down what time Saturday morning you want to come in and get your questions answered, okay? Because we don't have class time for that. Just keep that going through class. We'll start it over here to Johnny. Write down what time Saturday you want to come in, and I'll answer that question. All right. Now, we can answer stuff like this based upon that little cycle right there. Everything repeats in cycles of 4. Do you see how everything repeats in cycles of 4? It's just one 90-degree rotation followed by another, by another, by another. It brings us full circle. If I ask you to figure out what I to the 26,457th power is, all we have to do is keep this chart going until we get to 26,000, don't we? You want to do that? No. So real quickly, talk to your neighbor and see if you can come up with a better way to do that. Using what you know about how often I repeats. Go. What else could we do? Think about it. Talk to someone. Any ideas, Chris? You want to keep that chart going? Well, if you can't think of anything else, I would get that chart going. Because if the only tool you have is a hammer, you got to make everything look like a nail. So we got to keep that chart going at 26,000. I'll check back with you. What did y'all say?
Oh, if it's an odd number, then it's one of the negatives. So it's got to be like either -1.
If what's an odd number? What's your antecedent to it?
If the exponent.
Oh, if the exponent's an odd number. Oh, if it's an odd number, then it would have to land.
It would have to be either one of the negatives, either the -1 or -i.
How do we know which one? What'd y'all come up with? I saw y'all talking. Let's leave Jeremy out of this. Maybe he knows the answer already.
I don't know. I think Jeremy wants to look at it.
Look. If I to the 0 is 1 and I to the 4th is 1, what's I to the 8th? 1. What's I to the 12th? 1. What's I to the 16th? 1. Okay. If I to the 1st is I, what's I to the 5th? I. What's I to the 9th? I. What's I to the 14th? 13th. Sorry, I jumped ahead. It's I. Do you see a pattern there? Okay. If I have a large number and I know it repeats every 4 cycles, what really is the most important part of this number? What if I know that this goes into 4 evenly by a certain amount of times? Then what should it be if it goes in evenly? It should be a multiple of 4, right? And if it's a multiple of 4, it should be 1. What if it doesn't go in evenly? What if it has a remainder? What if the remainder is 1? If the remainder is 1, what should it be? I. What if the remainder is 2? It should be what? -1. And what if the remainder is 3? It should be -I. And what if the remainder is 4? Then you did the division wrong, right? Because you're dividing by 4. That was a trick question. Okay? So here's all you have to do. Divide by 4. The remainder is your new exponent on I. So it's going to be one of these. If your remainder is 0, it goes in evenly, it's 1. If your remainder is 1, it's I. If your remainder is 2, it's -1. If your remainder is 3, it's -I. And if your remainder is 4, you did your division wrong, right? Here are your remainders. Oops. 0, 1, 2, 3. All right, now try it out. Try 26,457. I'm going to do it quietly up here. You do it quietly at your desk. We'll see if we get the same answer. You get to do good old-fashioned long division here. What's that? We're right here. Yeah. Did I get a remainder of 1?
Yes.
So what should that I to the 26,457 actually equal? I to the first, which is I. Try one more here. Try I to the 8675308. We don't want to call Jenny. We don't want to bother her. Okay, try that one. 8675308. You definitely don't want to get the chart going here. You look for the remainder when you divide by 4, and the remainder is the new exponent. That Saturday morning card is finding its way around. Yeah, anytime. There's 24 hours in a day, so if your preferred time slot is taken. No, these have to be individual questions, individual consultations. You didn't realize you were going to be doing long division of whole numbers today, did you? You should already be on the division process. You're a little behind, Marcus. Yeah, so are you, what'd you get for your remainder? You got 2 for the remainder? Anyone else get another remainder? You got 0?
Yeah, I guess.
The remainder should be 0. It's a multiple of 4. Yeah. Yeah, you're off somewhere in that long string of you're off. Yeah. So you got to do the long division carefully. It's a meticulous process, but you should get a remainder of 0. And if the remainder is 0, then what is that equal to? 1. You could say this is equal to I to the 0, which is equal to 1. Okay? I to the 0, which is equal to 1. Now again, why is 4 the magic number to repeat the cycle? 4 different things. What are things? Coordinate. Quadrants is what you meant. Quadrants. There are 4 different quadrants, and we rotate 90 degrees through each of them 4 times. We arrive back where we started. And the algebra works out as well. Isn't that cool? How the geometric coordinates with the algebra. All right. Just a real quick little aside here before we move on. How would you graph a number that is purely complex? It has both real and imaginaries. Like a number like 1 plus I, you can't graph that on the real coordinate plane, but you can on the complex number plane. You would just come out 1 positive unit on the real number line, and then the coefficient of I is positive 1. So you'd go up 1 unit on the y-axis, which is your imaginary line, and you would draw a vector from the origin, the tail, and then the head is at the point 1, 1. And that line right there would be the graph of 1 plus I. Okay? We're not going to spend any more time in the complex plane. But I want you to know geometrically that they exist and that they are very, very, very real. In fact, your cell phones would not work without the power of imaginary numbers. Did you know that? Electrical engineering, replete with calculations that involve imaginary numbers. Okay, so next time you're on your phone, just be thankful for imaginary numbers. We're going to skip example 3 because it's just manipulating 2 complex numbers like you did in Algebra 2, and we're going to get enough practice in example 4. So let's jump to example 4. This is where the pre-cal jumps back in. Okay, so that was kind of an Algebra 2 review. All right, write a general equation for the polynomial function in reduced factored form whose only complex roots are -2, multiplicity 2, 2 minus 3i, and 2 plus 3i. Oh, and by the way, the right-hand behavior is negative. Okay, first things first. We want a general equation, so that's going to have our a in it. And then reduced factored form, remember, means the pretty form. So I'm going to start by saying f of x equals, I'm going to put the a in there to begin with. Now we use the factor theorem. If -2 is the root, what's the corresponding factor? No, the factor. X plus 2, thank you. If -2 is the root, the corresponding factor is x plus 2. And if it's a multiplicity 2, what's the exponent? Squared. Fantastic. Okay, now I have a complex root 2 minus 3i. The factor theorem then says that the factor is x minus the quantity 2 minus 3i. So just like last week when we had the irrational roots, remember we had the irrational conjugate theorem that said if a plus square root of b is the root, a minus the square root of b is the root, and we treated them like this when we wrote out the equation, minus parentheses, okay? X minus, x minus, x minus, that's always the factor. So the conjugate of 2 minus 3i, which is 2 plus 3i, is the root, so what's the corresponding factor? X minus parentheses 2 plus 3i, close, close. All right. So there it is in its prime factorization, but it's not in reduced factored form. Reduced factored form means we don't want any radicals and we don't want any i's in there as well. So guess what I have to do next with those two complex factors?
Multiply them.
I got to multiply them out. And I'm going to do that off to the side over here on my workbench because I don't want to have the burden of writing all that stuff equivalently. So let's go ahead and write down the two factors. We'll distribute as we write them down. Okay, let's distribute the negative. We get x minus 2 plus 3i and x minus 2 minus 3i. Now I just got to expand those out. Does FOIL work here?
Yes. No.
No, FOIL only works when we have a 2 by 2. This is a 3 by 3. You know what still works though? Distributing. Very good. Let's distribute. We'll start with the x here, and we'll distribute it all the way through to all three of those. So here we go. Start to the left. We'll go x squared minus 2x minus 3ix. There's distributing the x all the way through. Then we'll do the negative 2. We'll distribute it all the way through, and we get negative 2x plus 4 plus 6i. And then we distribute the plus 3i all the way through, and we get plus 3ix minus 6i minus 9i squared. So I color-coded it. We get 3 plus 3 more plus the final 3. This is the kind of stuff that example 3 that we skipped was. Okay, just manipulating imaginary complex numbers. All right, now I'm going to combine like terms. Let's start with x squared. Is there another x squared term down there? Nope, so I'm just going to single underline it and say it's done. Now, the x terms, I got a negative 2x and a negative 2x, and I got a positive 3ix and a minus 3ix. Hey, what happens with the 3ix terms? They cancel, okay? And I'm just left with minus 4x. Now, if you remember when we did this exact same thing with radicals last week, all the radical terms canceled when we expanded, right? The same thing should work here with your imaginary terms. All of your imaginary terms should cancel if you expand it correctly. All right, let's look at the numbers. Well, the 6i, I got a 6i and a minus 6i. Those are I terms, and guess what happens? They cancel. And now I have this minus 9i squared. What's another name for negative 9i squared?
9.
Positive 9, because I squared is negative 1. So now I have this 4 and this positive 9. What's 9 plus 4? 13. And there is the expansion of those two complex factors. I'm going to bring that back over here into my project. And now I have f of x is equal to a times x plus 2 squared times x squared minus 4x plus 13. Now I can't really find the value of a unless I'm given the actual point that it passes through, but I do know this. I do know that the right-hand behavior is negative, so what do I know about a? It's got to be a negative number, right? The leading coefficient, which is a, tells you the sign. So we'll just put comma, a is less than 0. And there you go. We just wrote our first equation giving two complex conjugate roots, right? What's the degree of this polynomial? No, not a 3. You have an x squared here in factored form, and then you have an x squared in the reduced factored form. 2 plus 2 is 4. It's a fourth degree polynomial. So how many roots does it have? 4. It has 2 real roots, right, with multiplicity 2? 2 real roots. And how many complex roots? 2. So by the fundamental theorem of algebra, am I done looking? Yeah, if you were to graph this fourth degree polynomial, you're only going to see a bounce at negative 2. That's it. It'll bounce at negative 2, and it'll wiggle off in space somewhere, and the 2 wiggles in space are going to end up being your 2 complex. Carly, did you have another question? Our negative 4x? Oh, because what's the degree of this polynomial? It's a degree 2. If you were to expand this completely out, what would the leading term only be? Remember, the leading term tells you what the degree is. That's going to contribute to a smaller degree term, right? The leading term here is x squared. That's going to give you x squared. X squared times x squared will give you x to the 4th. And that will contribute to like an x cubed term or something down the line. That's what affects the wiggles. Okay, we're all done. Real quickly here, as you're packing up, what's I squared equal to?
Negative 1.
What's I cubed equal to?
Negative I.
Negative I. What's I to the fourth equal to? 1. And what's I?
I.
It's I. Yeah, very good. Have a great day. Perfect timing.